Also very important. I'm gonna explain what does that mean, at least one. When you see those keywords in the problem, you are looking for something, at least one. Let me give you a very simple example. I have it here. I can use a different example. How about this one actually is a good problem. All right, so what happened is we're considering an experiment. The experiment is our day quiz. How many questions in our day quiz? 10 questions, right? 10 questions. Let's assume every question, all the questions are multiple choice questions. You should be very familiar with what's happening here. So in our day quiz, we have 10 questions. Let's say all of them are multiple choice questions. And for each question, there are 4 answer choices. Only one of them is correct, right? So here we want to consider the probability that you get at least one correct by guessing. Let's pretend someone never studied. They take the advantage of multiple choice questions. They just guess, randomly guess, okay? A, B, C, D. You have A, B, C, D. You randomly guess. You choose B, or next one you choose D. You just randomly guess the answer. Then what's the probability you guess one problem correct? C here means correct, the initial correct. What's the probability that you guess one problem correct? 1 over 4, right? 4 answer choices, only one is correct. So you have 25% chance to guess the question correctly, even you don't study. Then what's the probability that you guess the question incorrectly? W here represents wrong. You get it wrong by guessing, then that is 3 over 4. Because for each question, you either get it right or you get it wrong. They are complementary. So the two probabilities are supposed to add up 1. So far so good? So we are looking for the probability that there is a person. He takes the quiz, the day quiz, the 10 questions by guess, G-U-E-S-S, just randomly guess. What's the probability that he got at least one correct? He got at least one correct. At least one correct. There are 10 questions. What's the probability that he got at least one question correctly? Well, let's look at this event deeper, closer. Let's look at this event closer, this result. Get at least one correct includes get exactly one correct, right? 9 wrong. And exactly one correct could be the first one, could be second one, could be the last one. And in this case, the result also includes you get exactly 2 correct. The 2 correct may be the first 2, the last 2, any 2 among the 10. This result also includes you get exactly 3 correct. The 3 correct could be any 3 of the 10. It also includes you get exactly 4. Did I say 3? 3 correct. Exactly 4, exactly 5, exactly 6, exactly 7, 8, 9, or if you are lucky, 10 correct, right? Do you see how complicated this result is? Then we don't want to compute the probability of this event directly. We want to take we want to look at the opposite side of this event. We want to consider its complement. We want to consider is complement. What's the complement of get at least one? Correctly. Non-correct. Let's take time here. If this is A, this would be A bar. That's the reason the probability of A equals 1 minus probability of A bar. We talked about this before, right? And let me explain why the two events are complementary. I'm gonna bring in a random variable here. I'm going to numeralize the results. Let X be the number of successes. Let X be the number of successes among the 10 trials. You do the first question, that's the first trial. Second question is the second trial. The 10th question, that's the 10th trial, right? And X is the number of questions you get correctly by guessing. So all the possible values for X would be either 0. It is possible you didn't get any of them correctly, right? So X could be 0, or 1, or 2, or 3, 4, 5, 6, 7, 8, 9, or 10. No more than that. You only have 10 questions. Okay? So at least one, you get at least one question correctly. That includes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All those numbers covered by blue. Okay? Then what's the complementary result? Would that be 0? Is that understandable? So here we have a very, very important fact that you need to remember. The complement of at least one is none, or the complement of none is at least one. Sounds very catchy, right? But you do have to understand what does that mean. At least one means the value of X, the value of the variable X is bigger than or equal to 1. The complement must be X equals 0. That means none. You answer the 10 questions by guessing. None of them is correct. So please take time, maybe repeat this part. Really figure out how come the complement of at least one is none. The complement of none is at least one. Why those two events are complementary? At least one correct. Is complement is non-correct. This should be very clear. Okay? All right. So how do we compute the probability of none? You guess the 10 questions. You answer the 10 questions by guessing. None of them correctly. Means the first is wrong. The second is wrong. The third is wrong, and the fourth is wrong, and so on and so on. The 10th is wrong. Do you see what I'm saying? None of them is correct. Could be written as the multiplication of the 10 events. The first is wrong, and the second is wrong, the third is wrong, and so on, and the 10th is wrong. So we are looking for the probability of a multiplication. Did we learn multiplication rule? You remember when we apply multiplication rule, we need to figure out, are those events dependent or independent, right? You tell me, are they dependent or independent? Independent. They are independent, and why? We do not consider the psychological factors. We assume a robot is guessing the problems, okay? Just by pushing the button, or a monkey or an elephant. So those events are independent, because if the first question wrong or right, it doesn't affect if you guess the second question wrong or right. We do not consider the psychological factor. So they are independent. In the case of independent, this probability equals the probability of W1, first question wrong, multiplied by probability of W2, multiplied by, and so on, probability of W10. Okay? Alright, so what's the probability of W1? The first question you get it wrong. What's the probability of getting it wrong here? 4 answer choices. Only 1 is correct. So the chance you get it wrong is 3/4. Then what's the probability of the second question you get it wrong? Still 3/4. What's the probability of the 10th question you get it wrong? Still 3/4. So here we have 3/4 to the power of 10. Do you have a calculator? By using your calculator, you would know 1 minus 3/4 to the power of 10 is about equal to 0.9437. That's the probability that you complete the 10 questions by guessing. You get at least 1 correctly. It's pretty high, right? It is pretty high. Turns out, if you guess and you get none of them correctly, is a very small probability. The complement of at least 1 is none, right? If you guess 10 questions, none of them is correct. That probability is only 0.0563. It's about 5.63%. 0.0563, so yeah, about 5.63%. That is not very high. So yeah, it means if a person really gets none of them correctly, that's really not lucky. Really not lucky. Alright, so that is at least 1. I think I'm pretty clear about the example, but we can repeat. By repeating the same process, we could understand that even better. So here is the problem from the notes. If a couple plans to have 6 children, what's the probability that there will be at least 1 girl here? We are looking for there will be at least 1 girl, at least 1. We are looking for a probability of at least 1. Assume boys and girls are equally likely. Is that probability high enough for the couple to be very confident that they will get at least 1 girl in 6 births? Let's see how do we find the probability. I need enough space to write a solution here. Alright, so let me see what color. Red color. At least 1 girl, right? We are looking for at least 1 girl. Do you remember the process? That is too complicated to compute. Straightforward, right? To compute directly. So we consider use 1 minus its complement. The complement of at least 1 is none, so no girl. None girl or no girls. No girls. 0 girls. 0 girls. 0 girls means what? The first birth is a boy, B1, and the second child is a boy, B2, and the third child is a boy, and so on and so on, and the 6th child is a boy as well. So that is the probability of B1 and B2 and B3 and B4 and B5 and B6, right? 1, 2, 3, 4, 5, 6. Are they dependent or independent? We don't consider psychological factor or genetic factor or biological factors. We assume then they would be independent. Okay, if the first birth girl or boy does not affect the chance of the second time you get a girl or boy, so they are independent. That's the beautiful part. Because they are independent, we are able to apply the simple version of the formula of the multiplication rule. So that is P of B1 times P of B2 times, and so on, times P of B6, right? All right, what is P of B1? What's the chance or the probability that the first time the couple get a boy? Half. That is given in the problem. Getting boys and girls are equally likely. The probability of the second child is a boy, also half. Third boy is also half. Number 4, number 5, number 6. 1, 2, 3, 4, 5, 6. So that is 1 minus half to the power of 6. That is 1 minus 1 over 64. That gives us 33 over 64. It's a very high chance. If you express the fraction as a decimal, 63 divided by 64, that is around equal to 0.984375, so 44. Keep 4 decimal places. Yeah, that's a very high chance. Okay? Can a couple be very confident that they will have at least one girl? Yes, because the probability is very close to 1. The more you give birth to, the bigger chance that you have at least one girl, right? Yeah. No girl turns out is a low chance. But I know people that they have 7 girls or 7 boys. That also happen. As long as the probability is not 0, it could happen, of course. This is the procedure of finding the probability of at least 1. We actually applied the procedure twice for the previous 2 examples. All right, next topic, permutation and combination. Permutation and combination. I consider to give you 3 examples to help you to understand what is a permutation and a combination. How about let me start another video to explain what is a combination and a permutation. Before that, I want to recall what is a fundamental counting principle, because the fundamental counting principle is the basic of understanding permutation and combination. All right, so yeah, we can read the 3 definitions first before my 3 examples. Fundamental counting principle or counting rule. M times n equals the number of ways that the 2 events could occur, given that the first event could occur m ways and the second event can occur n ways. This rule extends easily to situations with more than 2 events. Example, for a 2-character code consisting of a letter followed by a digit, the number of different possible codes is 26 times 10, which is 260. Why? This is the pin you will consider, right? The first thing is the first character is a letter. How many letters do we have? 26. We all know that, right? So we have 26 different options for putting a letter here for the first character. And the second character of the pin or the code is a digit, 1 digit. How many digits do we have? We have 10. There are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is not. 10 is a 2 digits number. Okay, so that is 10 already. So we have 10 options for the digit. That's the second character in the code. So 26 times 10, that is 260. So if someone steal your card and use the 2-character codes, they would have to guess 260, maybe at the most 260 times to get a correct pin. Alright, permutation and combinations. Let's understand or try to understand the definition, the formal definition. Permutations of items are arrangements in which different sequences of the same items are counted separately. For example, with the letters ABC, the arrangements of ABC, ACB, BAC, BCA, CAB, CBA are all counted as different permutations. You know, to make this simple for you, in permutations, order matters. Don't forget the two keywords, okay? In permutations, order of those items matters. So that's the reason those 6 arrangements are counted separately as 6 different permutations. While in combinations, order does not matter. So order does not matter when we consider combination. Combinations of items are arrangements in which different sequences of the same items are not counted separately. For example, with the letters ABC, the arrangements of ABC, ACB, BAC, BCA, CAB, CBA are all considered to be same combination. Alright, so remember the two keywords for identifying permutations and combinations. I'm going to give you 3 examples to help you understand permutations and combinations in the next video.